Okay, so this is now number 2. This is a calculator aloud problem. Consider the closed curve in the xy plane given by x squared plus 2x plus y to the fourth plus 4y equals 5. Now, again, it's important to recognize that this is an implicit function. So this is just some ambiguous curve. We start. Show that dy dx equals this simplified answer. Now, this is something you should know about the AP test. When they do this, and they say dy over dx equals this, they're giving you this answer because if you accidentally do something wrong when you do the derivative, you won't mess it up later on. So it's really nice that they're doing this for you. They're just testing, do you know your implicit differentiation? So that way when you get answers later on, you get to use this, which has nice properties of the numbers they pick match up pretty well. So we're going to start with x squared plus 2x plus y to the fourth plus 4y equals 5, taking the derivative in terms of our buddy x. Now, I looked at this problem and I said, you know what? I see x squared by itself, 2x, y to the fourth, 4y, and 5. The nice thing about that is there's no product rule involved. And a lot of times with implicit, there is product rule or chain rule. In some problems, you get away with it, and it's just something nice to recognize, and it's important to kind of see that on the front end. Let's take the derivative. X squared, 2x. 2 is just 2. Y to the fourth is 4y cubed, but since it's in terms of x, we have to leave a dy dx hanging out. Derivative of 4y is 4, but again, it's in terms of x, so we got to do dy dx, and that equals 0. Now, how do I get dy dx by itself? Well, simple. Subtract these guys. So we have 4y cubed dy dx plus 4 dy dx equals negative 2x plus 2. Next, you always remember the property that if I have 2 dy dx's and I'm trying to solve for it, let's factor dy dx out. So I have 4y cubed plus 4 equals negative 2x plus 2. Let's move the work up here. Next, get dy dx by itself. Divide over the 4y cubed plus 4. So dy dx equals negative 2x plus 2 over 4y cubed plus 4. Now, this is where we came up with dy dx, but clearly the answer is a little different. So we kind of have to match up the algebra here. How do we get a negative parentheses x plus 1? Well, we take a look at this. If we want an x plus 1 on top, we're going to have to factor out a negative 2. Because that would... Oh, I just realized I made a mistake. Here, it should be 2x minus 2. 2x minus 2 and 2x minus 2. And if I factor out a negative 2, then I get a plus 1 here. So again, even if I make a mistake, I can quickly recognize what the mistake was and fix it. Because again, if I have the wrong derivative, all my other answers can come out very ugly. On the bottom, well, I want a y cubed plus 1, so they probably factor out the 4. 4 times y cubed plus 1. And finally, let's see, negative on top and 2 on the bottom, well, they probably reduced. So that's negative x plus 1 over 2y cubed plus 1. So there is my derivative of y in terms of x. Very nice, because from now on out, I know I'm going to get the right answer for the derivative. All my other answers aren't going to be screwed up. Write an equation for the line tangent to the curve at the point negative 2, 1. They already gave me the point negative 2, 1. The one thing you should not do, so I'm intentionally going to write this in something you should not do, f prime of negative 2. There was no f, and this is not a function, this is implicit, so don't do this. Instead, I'm evaluating dy dx at negative 2, negative 2, 1. I'm using both, x and y. Well, plugging it in, I'm going to have negative 2 plus 1 on top, 2, 1 cubed plus 1 on the bottom, which, if I simplify that, that's going to give me negative 1, which turns into a positive 1, over 1 cubed plus 1 is 2, so that's a 4. So the equation of the tangent line is y minus 1 equals 1/4 x plus 2. Again, you can't just write 1/4. You have to tell me where you're getting 1/4 from. You're evaluating dy dx at negative 2 comma 1. Find the coordinates of the 2 points. It's telling you 2 points, so you don't screw that up. On the curve where the line tangent to the curve is vertical. Well, what do we know? If the tangent line to the curve is vertical, dy dx is undefined. What does that mean? I have something on top and I'm dividing by 0 on the bottom. So when I look at what dy dx is, I really just care about that denominator, which was 4 times y cubed plus 1 equaling 0. A little bit of algebra. Y cubed equals negative 1. Divide the 4, subtract the 1. And then cube root both sides. Well, that still leaves y equal to negative 1. Now, always, once you get this y equals negative 1, it's saying find the coordinates of the 2 points. I do need x. Where do I get x from? The original equation. So x squared plus 2x plus y to the 4th plus 4y equals 5. Let's write that down. X squared plus 2x plus y to the 4th plus 4y equals 5. All I'm doing is I'm evaluating this at y equals negative 1. X squared plus 2x. This is going to give me positive 1 minus 4, which is negative 3, equals negative 5. Oops, positive 5. Subtract the 5 is what I wanted to say. Factor this, x plus 4x minus 2 equals 0. And this is a calculator log problem, so you could have gotten the answers from there. So then I know x equals negative 4 and x equals 2. It wants the coordinates answer their question. The two coordinates are negative 4, y was negative 1, and I'm going to try to squeeze it in, positive 2, comma, negative 1. All right, last. Is it possible for this curve to have a horizontal tangent? Horizontal tangent, that's important. It's not something you can overlook. It has to have horizontal tangents at points where it intersects the x-axis. If I take those two ideas and put them together, then actually it gives me everything I need to know. So this isn't something you should just read and overlook the big details. It's really important that you see horizontal tangents, which means dy dx equals 0, and intersects the x-axis. Intersects the x-axis means it's an x-intercept, which all x-intercepts have this property, y equals 0. Simply writing y equals 0 could have given you a point. Or you could have done dy dx equals 0 and solved for whatever x or y could be. So if I look at what dy dx is, it's negative x plus 1 over something. But again, if we know the derivative is equal to 0, we only care about the numerator. Solve for x, you get x equals negative 1. So I also know that x equals negative 1 or y equals 0. Well, since there's no combination besides just negative 1 is 0, this would have to be the point of the horizontal tangent that intersects the x-axis. But all I did was interpret information that's partial. Some information here, some information here. I don't know for sure if this is a point on the graph. So I have to look back at this and I say, okay, x squared plus 2x plus y to the 4th plus 4y equals 5 is the actual curve. I'm going to plug this in here, because if it's a true statement at the end, then it's an actual point. If it's not a true statement, then the question, is it possible? The answer is no. So plug in x equals -1, so -1 squared plus 2 times -1 is -1. And all the y's cancel. Is -1 equal to 5? I don't think so. So therefore, no. Since -1 comma 0 is not on the curve. Now, I can say that because all my work shows me where I got -1 comma 0 from, so that part's justified. There are many, many different ways of showing this. One way is starting with x equals -1, plugging that into the original curve without the y equals 0, and figuring out will y be 0. Another thing you could have done is start with y equals 0, plug it in here, and then once I have new x values, plug them into the derivative to figure out if I'm going to get a derivative equal to 0. Either way is fine, but this is the actual easiest way. And it's simply because I really read carefully what it was trying to do.